Okay, so I left you to look at this light curve from one of these type 1a supernovae that we were discussing in the last lecture, and to work out the distance to this particular supernova in a particular galaxy a long, long way away. So you can see that here's the peak of the light curve is here. So the sort of maximum brightness, if you like, is 18.0, give or take, on that scale. Okay, so that's what we would call the apparent magnitude at the maximum light in the light curve. And conveniently on the right-hand scale here, we've also got the absolute magnitude scale calibrated for these type 1a supernovae. And so the idea is that this maximum light here, so the absolute magnitude of that, which is given here as the absolute magnitude minus 19.2, don't forget the minus sign, very important. So the minus sign telling us that these objects, these exploding stars are incredibly bright. Okay, minus 19 is very, very bright. Okay, so that's the absolute magnitude at the maximum brightness. So then again, we just need to apply this formula and put in the numbers, and you'll see the distance you get is now 250 megaparsecs. Okay, so this is 20 times further or so away than the Virgo cluster. So we're really stepping out into the universe now. Okay, and here is the picture of the host galaxy where this supernova went off in. So it went off in the outskirts of that galaxy there. Okay, you can see that it's a barred spiral by the looks of it. I'd say that was an SBA or something like that. Okay, so you can see the size of it here. So just over 28 seconds across or something like that. Okay, so you can still make good images of galaxies even when they're this far away, and later on we'll see even when they're much further away than that. Okay, so that's kind of where we're going next. Is how do we another way of looking at distances to galaxies, really, and leading us on to talking about the entire universe, the expansion of the universe, and at the end of the lecture we'll have a look at the age of the universe. So this is going to take us towards the Big Bang. Okay, so the first topic we want to look at here is this idea of redshift. But here this is in the context of the redshift of galaxies. Okay. So we've kind of met this several times before now, but let's formally define it once again. And we're going to introduce a sort of a new terminology here, which is used in extragalactic astronomy. So the idea of the Doppler shift, redshift, being measured as Z. And here Z is, again, this is a very similar formula to I think that you've used a few times before. So this is the term in the Doppler shift. Okay, so this is basically the fractional change in wavelength due to the relative motion of a galaxy this time relative to rest. Okay, and as always with Doppler shift, you need a spectral line. So you're talking about the wavelength as observed of a particular spectral feature in the spectrum of a galaxy now. Okay, compared to the lambda naught, the rest wavelength, so the wavelength that line would have if there's no velocity between the emitter and the observer. So just again, delta lambda over lambda naught, where delta lambda is the observed wavelength minus the rest wavelength, all divided again by the rest wavelength. So here we're going to define just this term as Z, the redshift of the galaxy. Okay. And then the more common Doppler formula that we've been using already. So V is just delta lambda over lambda naught times C. That now becomes C times Z, because Z is what we've just defined to be delta lambda over lambda naught. So it's not really anything new here apart from the terminology introduced by list Z, the redshift. Okay. So just a note here that this particular version of the Doppler shift is obviously just the normal classical Doppler shift. We shall see in a moment that the velocities that galaxies are receding away from us can get extremely high and even close to the speed of light. And in that case, this formula is not appropriate at all, and you have to use a relativistic version of the Doppler formula instead. Okay. And that's because you might hear in the literature or the news about galaxies with redshifts greater than 1, which obviously for this formula doesn't make any sense because nothing can travel faster than the speed of light. So when you hear about galaxies with a redshift greater than 1, it doesn't mean that. It means that their redshift has been determined using the relativistic version of this formula, which I'm not going to bother you with in this module. Okay, so how do we measure the Doppler shift of a galaxy? Same way as we measure the Doppler shift for anything else. Okay, but I wanted to show you some real data here. So again, this is from another of these sort of fantastic modern observational astronomy projects called the Sloan Digital Sky Survey. So again, this is where the Sloan Foundation, so a private foundation in the US, has funded a dedicated telescope to basically take spectra of galaxies and measure the spectra of basically 1 million galaxies. Okay, and it does this by using sort of clever fiber optics. So you you put a fiber on a particular image of a galaxy in the focal plane and feed that fiber into a spectrograph, and you can have hundreds of fibers all feeding one spectrograph at the same time. And so you can place those fibers anywhere in the field of view of your telescope and grab hundreds and hundreds of spectra at the same time, exposed for quite a long time because you're trying to go faint to get faint galaxies. And that telescope just operates night after night, just harvesting redshifts of galaxies. Okay, so here is the spectrum in white. Okay, don't worry about what the scale is here. This is uncalibrated. And just a word of caution that again, this is an optical spectrum. The wavelength here is in angstroms, and so if you want to convert back to nanometers, you need to divide by 10. Okay. So this is the optical spectrum range as usual. Okay, but you will see lines that are normally at the blue end, like H beta here. So H beta is normally down here at 4,800-ish angstroms, is redshifted all the way up here to the red end of the optical. Okay. And similarly here, the sodium D line, the nice orange line that you have in streetlights, so again, normally that would be here at 5,800, is shifted all the way up here. In fact, pretty much out of the optical range altogether. Okay. So that's what's going on here. So just so you can interact with this data yourself. Here's the rest wavelength a bit more accurately for H beta, 4,861 angstroms. That's the symbol for angstroms, and there are 10 angstroms in a nanometer. But again, don't worry about that. Why don't you just have a go at working out the redshift of that galaxy on the previous slide yourself, just by reading the information off the scale. Okay, so have a go at that, and we'll come back after the break.